Okay, well, it's our last class for the semester. We have the exam, which is Wednesday morning. As far as a review is concerned, there will be something for the last chapter we're just working on. As far as the other chapters, I think just going back and watching the reviews for the previous tests is a good thing to do, especially things that you maybe didn't do so well on. The homework for chapter 9 will be due at the exam. So I'm assuming mostly what you guys will do is you'll study for calculus. You'll take your calculus test, then you'll have a day and a half to finish your physics homework up and study for the physics exam. Now, most of you are in my calculus class, so what was I going to tell you about that? Oh, I know what I was going to tell you. So there are 15 problems on the calculus exam. And there's one thing in the modules. I went through this the other day, but I did a special video on this because in the past I haven't had time to review it, but there's an exam. One says limit definition for exam. So this is using the limit definition for the derivative. So if you want to review that as well as the tests and the videos, here's an equation sheet if you need it. And I'll start the exam both for physics and calculus at 7:30 if you want to. You know, I'm assuming you don't have anywhere to go to until 10:30, 11 anyway. So you should have, probably give you till 11 o'clock. So that's three and a half total hours possibility. It's, obviously it's not going to be that, won't take you that long if you know what you're doing. Some of you probably just wish that I would make it 2 hours so you could have yourself put out of your misery and shut the thing off. But anyway, for you guys who are slower workers, you should have plenty of time. I have finished grading the calculus tests. I hadn't done yesterday, but I was going to wait till after class today to post them. Let's see if Hannah's here. Nope. McKaylin. Okay, McKaylin. Question: how many problems are on the physics final? I just think I haven't made the physics final up yet, but based on previous years, it's usually about 9 problems, 2 from the most recent chapter, and then 7 from previous chapters. Okay, so let us finish up. So we've talked about the deformation of solids as you apply a force to either end, and we've looked at that, the very specific case of a uniform material that has a uniform cross-sectional area. It's constant force. And the main thing out of that was the stress. Stress was equal to the modulus elasticity times strain, and the stress is the force divided by the cross-sectional area, and the strain is the change in length divided by the original length. So it's just a matter of manipulating that equation for whatever I don't give you in the problem. The second thing was, as far as hydrostatics, there's 2 things. One is that the pressure at some depth is the pressure at another depth plus the density of the fluid times the acceleration due to gravity times the height difference between the two locations in the fluid. And the second one is that the buoyancy force is equal to the density of the fluid that's being displaced times the acceleration due to gravity times the volume displaced. Okay, so this is called hydrostatics. Hydro because it's a fluid. Statics because nothing's moving. The third topic is what's named Bernoulli's equation. And what this has to do with is fluids that are moving. So, you know, a typical example looks like this. You've got fluid inside of some kind of enclosed channel. You can think of it like a hose. That's probably the most, or water going through your pipes in your house. And of course, what we're doing here is this is connected ultimately back to the water plant, and this side is connected possibly to just a tank or to the outside. And what we do when we deal with this situation is you've got we draw what's called a control volume. So I'm going to draw this little dashed line around this part like this. So this little, and it's not a real surface, it's a figurative surface. So we're going to call this the control volume. It's volume because it's a three-dimensional space, so it's a volume. And control just means that we're separating that from everything else. So what you have here, we'll call this the inlet and the outlet. Okay, so that's where the fluid comes in. So you can think of water flowing here. And what these arrows represent are the velocity. So we'll say V sub I. So let's make a little space here. So VI equals the inlet velocity. This is normal velocity, has units of meters per second. But instead of being like a solid body, that's what we've been dealing with in the past, is a solid body. We're talking about a little particle of water or air that's crossing this boundary. So if you got a hose running, it's not the same water every time. We don't look at a particular point of water. You know, you've got a little water particle here, and it's going to move through here at various times. And then a different particle will move through, and so forth. So it's never the same particle, but a lot of times it's the same area that we're looking at, or the same volume we're looking at. Now on the outlet, you're going to have a velocity as well. So this is, again, these arrows are to represent velocity. So V's out. We'll call this the outlet velocity. Units of meters per second. So the question I have for you is, which is greater? This is a chat window question. Which is greater, V sub I or V sub O? Question mark. You get a 50% chance of it being right. Okay, so we got, most people are saying VO. Well, that is the correct answer, okay? So the answer is V0, which is the outlet velocity. Why is that? Well, because if I have a certain amount of fluid flowing in this inlet, which has a bigger area, so because I've drawn this bigger, and this is a smaller area, then to get the same amount of mass flowing through this surface, this is a pipe, so it doesn't, the mass can't go out here because it's a solid surface. But here it's, it's like if you cut a pipe and you broke a pipe, you'd have, that's where the fluid can go in, that's where it can go out. So there's less area here, and therefore the velocity has to go up to be able to have the same amount of stuff pushed through this surface as through this surface. So there's actually another equation which I didn't mention, but I'm going to now, which is called conservation of mass, or we'll say mass flow rate. That's so what is mass flow rate? Well, what do we use for that? Well, we use m with a little dot over top of it. Okay, this is another terminology. We haven't used this in calculus yet, but if you put a dot over a letter, it means the rate of change. So this is going to be kilograms per second, saying there's so much mass that crosses this boundary here per second. Like 100 kilograms of water is passing through this boundary. 100 kilograms also has to leave this one per second. They have to be equal to each other. So what conservation of mass says is the mass flow rate coming in has to equal the mass flow rate going out. What comes in must go out. The only way that wouldn't be true is if you had holes in your pipe, or if you could compress, if this fluid were compressible, you could possibly have a difference. But that would only be that would actually only be in for a small time period. Okay, so mass in equals mass out. So what is that in terms of the variables? Well, I'm going to write it out as this. You've got the density of the fluid coming in times the velocity of the fluid going in times the cross-sectional area in the input, in the inlet. And that's equal to the density going out, the velocity going out, and the area going out. Sorry, these all should be outs. So this is density. We've talked about that before, I think. Yeah, we did. Density, that's kilograms per meter cubed. V is the velocity. That is units of meters per second. And area, that's area, cross-sectional area. And that has units of meters squared. So you can see from a unit standpoint, I'd have kilograms per meter cubed times meters per second times meters squared, and these cancel out with those, and you get kilograms per second. So that's in terms of the properties of the fluid, the density of the fluid, the velocity of the fluid, the cross-sectional area of the pipe, the same on the other side. Now, if the density is constant, which happens a lot, or is constant or relatively constant, then these two cancel out. That means the density in equals the density out. And so you can say conservation of mass is velocity in times area in is equal to our input inlet, velocity outlet times the area of the outlet. So if we solved for V out is equal to V in times A in divided by A out. So that helps us answer our question earlier. I said which one was bigger, V in or V out, or which was greater. Well, if the area coming in is bigger than the area going out, then the velocity has to increase. If it goes the other way, then it decreases. I could flip this thing around. This could be the inlet, and that could be the outlet. Okay, so that's conservation of mass. We won't worry about density in this class. If you become a mechanical engineer or an aerospace engineer, you'll worry about density, but we're just going to, actually that's more this equation. They're the same equation. Okay, so that's conservation of mass. Let's add a page here. Now the next thing is Bernoulli's equation, which I've already written it down, but I'll write it down again. There actually were a couple of Bernoullis. It's kind of like there were a couple of Bachs, you know, in terms of music. So there are a number of Bernoulli brothers. So when you see something with the name Bernoulli, and we will see this in second semester calculus, there is a thing called a Bernoulli something or other. And I think I might have put an extra I there. So anyway, don't always assume that if you hear Bernoulli, it's one person. Okay, Bernoulli's equation. Let's draw this picture again. So again, it's a pipe that gets smaller, and the fluid is flowing in here, and it's coming out there. And I'm making this arrow bigger. So again, this is the in. You don't have to redraw this. I'm just redrawing it because I don't have another page. Okay, and there was an inlet area, and there was an outlet area. Now it turns out you can also have a pressure at the inlet, and you can have a height at the inlet. And you could have, I'm drawing this as all being on one height, but it could be at a different height. So let me define these variables. P is pressure, which has units of newtons per meter squared, force per unit area, and that has the units of pascals. And H is the height, and that has units of meters. So there's a height for the inlet, there's a height for the outlet, there's a pressure for the inlet, there's a pressure for the outlet. There's a velocity for the inlet, there's a velocity for the outlet. Now, Bernoulli's equation is basically conservation of energy for fluids. We haven't done conservation of energy yet, but it is when we get to that. Well, we have done conservation of energy. We've done like conservation of mechanical energy. If you remember back here, remember conservation of mechanical energy. This was chapter 5. We had 0 is equal to the change in kinetic energy plus a change in gravitational potential energy plus a change in spring potential energy. So that's our conservation of energy thing that we've done so far. Now, if you apply this, we don't have springs per se in fluids, except we do have pressure, which kind of acts like a spring. So here's Bernoulli's equation. It says P inlet over rho inlet plus 1/2 V inlet squared plus GH inlet is equal to P outlet over density outlet plus 1/2 V outlet squared plus GH outlet. So this is kind of like the energy coming in per unit mass, because you see instead of having one, here kinetic energy normally is 1/2 mv squared. You have to just get 1/2 v squared. So this is kind of like energy per unit mass. And again, you can check let's check the units here, see if those make sense. So pressure is newtons per meter squared divided by density, which is kilograms per meter cubed. Here we have meters per second squared, and here we have meters per second squared times meters. So these are the units. So these are pretty obviously the same. Meters squared per second squared, right? Meters squared per second squared. Meters squared per second squared. Now over here, it's a little less obvious, but you know, a Newton is equal to a kilogram meter per second squared. Force equals mass times acceleration. So we could replace Newton with kilogram meter per second squared divided by meter squared, all divided by kilograms per meter cubed. So the thing we could do is we could take the reciprocal of this, get rid of that. So these cancel out. And then what this would do, this would cancel out with two of those. So here you'd have meters squared per second squared. So it's the same units. So I did remember that correctly. Okay, so they are all the same units. Let's just erase that. You don't need to know that. I just want to show you, convince you that they were actually. Oops. Anyway, they are the same units. Now, to do Bernoulli's equation, you do need the density. I mean, you can't. Well, you wouldn't need density if density was if there was no change in pressure. But if you do have change in pressure, you do need density. Whereas in conservation of mass, if the density is constant, we don't need it. It cancels out. But for Bernoulli's equation, you do need density. But you can see how it, 1/2 mv squared, gravitational potential energy is mgh. So you just got this extra term, which is kind of sort of analogous to spring, but not necessarily. How many people, this is a chat window question for you. How many people remember talking about enthalpy in chemistry? Okay, so you, sadly, that's funny. Not entropy. Entropy is another thing, but enthalpy. You might have talked about entropy in chemistry, but there was this enthalpy. So this actually in mechanical engineering, when you take thermodynamics, you actually, the enthalpy is defined as the internal energy plus, what was it? The pressure times the divided by the density or something like that. So internal energy is kind of like the energy associated with the random movement of molecules. Pressure is a bit different. So Bernoulli's equation, if you use Bernoulli's equation in mechanical engineering where you actually have like steam or something that's expanding, you actually use enthalpy here. I don't remember exactly where the density comes in. I think it's enthalpy plus 1/2 rho v. So if I use density here, anyway. I could look it up, but I don't. It's been a long time, 30 years. Can't remember everything. Okay, so anyway, you don't have to, we're not worried about enthalpy. If you don't want to hear enthalpy, don't become a chemistry major or chemical engineer, mechanical engineer. You'll see it again. Okay, anyway, this is Bernoulli's equation. So let's just do an example using these two equations. Bernoulli's equation, conservation of mass. Okay, so we're going to do water. Let's say water flows into this configuration with a velocity of 1.5 meters per second. Okay, so that's my inlet velocity. It's 1.5 meters per second. And I'm going to specify the area. The inlet area is, well, let's go ahead and use diameters instead. Let's assume it's a round pipe. Give some practice calculating the area here. The inlet diameter is, let's see, get my ruler out, give some reasonable number. Let's say it's 6 centimeters. Or, yeah, 6 centimeters. The outlet diameter is 2.4 centimeters. What is the exit velocity and pressure assuming water is incompressible, which is a pretty good assumption. Incompressible just means density equals constant. Okay. So how do we do this thing? So we've got the inlet diameter. What did we say? Diameter equals 6 centimeters. The outlet diameter equals 2.4 centimeters. So the way you work this is you do conservation of mass first, because I can calculate the areas based on these diameters, well, assuming it's a circular cross-section. I know the inlet velocity, so I can use conservation of mass to calculate the outlet velocity. So that's the first thing we do. So let's calculate the inlet area. It's going to be equal to pi 6 centimeters would be 0.06 meters divided by 2 squared. It's going to be small area. So we get pi times 0.06 divided by 2 to get into radius squared. Okay, so we get 0.00283. I'm going to take one extra significant figure here. Meter squared. The outlet area is 0.024 meters divided by 2 squared. Pi times 0.024 divided by 2 squared. So there we get 0.000452 meters squared. Okay, so those are the inlet areas. So we said conservation of mass says that V inlet times A inlet equals V outlet times A outlet. And so if we solve for V outlet, is going to be V inlet times A inlet divided by A outlet. So we can stick the numbers in. What was the velocity coming in? 1.5 meters per second. The inlet area was 0.00283 meters squared divided by 0.000452 meters squared. So it's going to go up. And I realized I got one more thing I need to give you guys. Okay, so the outlet velocity is 9.4 meters per second. So it went from 1.5 to 9.4. And you can actually figure that out if you could just take the ratio of the diameters. So if you take 0.024 divided by 0.06 and you square that, you'll get, wait a second. No, you got to square them and then divide them. 0.024 squared divided by the other way around. No, that's right. 0.024 divided by 0.06 squared. Well, it should be the same thing. 0.16. So if you divide 1.5 by 0.16, we should get 9.4, which we do. Okay, rounds off to the right answer. Okay, so you can see the velocity's increased. The only thing I didn't give you was the pressure coming in. So let's say that the pressure in is going to be equal to 300 kilopascals. So it's, remember, about 100 kilopascals is atmospheric pressure. So it's a little less than 3 times atmospheric pressure. So then you can use Bernoulli's equation. So that says P inlet over rho plus 1/2 V inlet squared plus GH inlet equals P outlet over rho. I'm just putting rho because the density doesn't change, and we know the density of water. So it's kind of like with conservation of energy. A lot of times you can cancel stuff out. H inlet equals H outlet. So those are going to go out. The density of water is 1,000 kilograms per meter cubed. What do we know? Let's check off what we know. We know the inlet velocity, we know the outlet velocity, we know the inlet pressure, we know the density. So you can see the only unknown is the outlet pressure. So let's do this algebraically. If we multiplied everything by rho, we'd get P inlet plus 1/2 density times V inlet squared is equal to P outlet plus 1/2 rho V outlet squared. So if we solve for P outlet, move this to the other side, we'll get P inlet plus 1/2 the density, and we'll have the velocity in squared minus velocity out squared. So all I've done there is move this to the other side, so it becomes negative. Because you've got 1/2 and you've got density, common factor, I factored it out. So now we just plug the numbers in. So the inlet, we got to make it into pascals, 300,000 pascals, 300 kilopascals, plus 1/2 the density of water, which is 1,000 kilograms per meter cubed. The inlet velocity was 1.5 meters per second. Quantity squared minus the outlet velocity, which is 9.4375 actually, but we'll put it 4 meters per second. Quantity squared, and see what the answer is. 300,000. Why don't you guys put the answer in the window? Oh, answers, I just don't, oh, there we go. We're starting to get answers with lots of significant figures. That's fine. Okay, so the answer is to two significant figures, 260,000 pascals or 260 kilopascals. So yeah, that's how it works with Bernoulli's equation. So this is an example, kind of example I could put on the test. It's pretty straightforward. I've just done the example for you. Now there's one other example that I want to do, and it's actually, I may not work through the whole thing because the homework problems relate to this. This is something you can, I usually do a demonstration in class, which the students find funny. So I may do this in one of the lab classes next semester. So this is just like a bucket, and you fill it up with water, and then you put a small hole right down here at the bottom, and then the water comes out, and it actually goes like that. That's probably, let me redraw that. And then it hits the floor. So the question somebody could ask you is, where does that little puddle land based upon the height of the hole in the tank relative to the height of the fluid in the tank? This comes down, it's two problems really. There's the problem of what is the velocity of the liquid as it comes out the hole, which is where you use Bernoulli's equation. And then this one you can just use using chapter 2 stuff, or projectile motion. So if it comes out of it comes out like this, it's going to follow the shape of a parabola, and it's going to be, if you just threw something, a solid, if you threw something at the same speed as the liquid, it would follow the same path. Even though this is liquid, in terms of through the air, as the liquid goes through the air, it behaves like a projectile. The reason students find it funny is because it looks like, if you do this, it looks like you're peeing or something like that. But anyway, so how would you use Bernoulli's equation to address this? Well, if I blew up this little hole here, what happens is the liquid comes out like that. It actually has a contraction as it goes out this hole, but that doesn't matter. At some point, you come out to atmospheric pressure through this hole. And up here, if the tank is open to the atmosphere, this is atmospheric pressure as well. And with fluids, what we do is draw this control volume, even though it's not a pipe. So you draw a control volume like this, and you look at this fluid, and you apply Bernoulli's equation. So we would say this is the inlet and this is the outlet. The inlet is actually just atmospheric pressure. So what we can say is that, you know, P inlet equals P outlet, which is the atmospheric pressure. We can also say that V inlet is much smaller than V outlet. So that means we can approximate, we can say V inlet is approximately equal to 0. You know, it's going to be moving down slightly, but if this is a really small hole, then it's going to behave this way. You know, this velocity is going to be much higher than this velocity, and so you can assume it's negligible. So if we apply Bernoulli's equation, P inlet over rho plus 1/2 V inlet squared plus GH inlet is equal to P outlet over rho plus 1/2 V outlet squared plus GH outlet. We said this one goes to 0. These are equal to each other, so they cancel out. So if we solve for V outlet, we'll get GH outlet minus GH inlet. Did I get that the right way here? V outlet, no, it's the other way around. So it's VH inlet minus H outlet. And if you solve for velocity, you'll get it's equal to the square root of 2, multiply both sides by 2 times G times H inlet minus H outlet. And in terms of my little drawing here, it's just square root of 2GH. So you can predict what this velocity of the fluid coming out of this hole is using Bernoulli's equation. Interestingly, it's the same velocity. If you took a ball and let it fall here, you know, the velocity of this ball falling through this distance outside the tank would have the same velocity as the fluid that's coming out horizontally. So you could use conservation of energy to figure out what this, you know, if this were V0 equals 0, this is initial velocity, meters per second, you could say that V final would be equal to the square root of 2GH. Same, you get the same result. One through conservation of energy for a solid and one through Bernoulli's equation. So that's kind of interesting. One last example before we go to a handout is airplane wings. You know, why do airplane wings work? You can explain it using Bernoulli's equation. So what you have is you can have a stationary wing with air going by it, or you can have a moving wing with going into stationary air. And what happens is, you know, these are just representing the velocity of the air as it goes around this wing. And let's say this is my, I'll call that, this is, you can use Bernoulli's equation for external flow. This is not internal flow, but it's external flow. You can kind of use it as qualitatively looking at things. So this is the inlet velocity. So let's assume that this wing is stationary and you're blowing air past it. Well, because you're pushing this air to either side of the wing, you've got more air that has to go through a smaller area here. So the velocity here is greater than the air that you're pushing by the wing initially before it hits the wing. And because this velocity is higher right here, it means that the pressure here is less than the pressure in out here. Let's call this, that's just atmospheric pressure. So locally around the wing, the velocity goes up and the pressure goes down. Now with this symmetric airfoil, nothing happens. Your pressure gets lower here and your pressure gets lower there, and so the net pressure difference doesn't cause the wing to do anything. It just sits there. It gets pushed back because of drag. But what happens with a wing is there's two things you can do. One is you can take the same wing shape, which I didn't do a very good job there. Let me try it again. Is you can put the wing at an angle like this relative to the flow. And what happens there is this stuff goes around, again, around the airfoil. We're assuming that. So what'll happen here, we'll call this the top, and this is the bottom. So P top is still going to be less than P outside here. The pressure in the air out in the regular air, atmospheric pressure. And the pressure on the bottom is still also going to be less than atmospheric pressure, but P bottom is greater than P top because of the way this wing is inclined at an angle, and this has to go further to get to the, for this air to meet at the end, at the back of the wing. This one has to go further, has to travel a further distance than the one on the bottom. So since it has to travel a further distance, it has to go faster, and because it's going faster on the top than it is on the bottom, the pressure on the top has to be lower than the pressure on the bottom. And that pressure difference acting over the surface of the wing causes there to be a lift force. So that's one way of doing it. The other way is to not have a symmetric airfoil, but to have an airfoil that looks kind of like, that's not very good. Let me try again. Wait till I finish before you try drawing this. So you got the front, and I'm going to kind of exaggerate this, but what you do is you have curvature to the wing. So when this air comes in, because of the curvature, it has to go at further distance around the top than the bottom. Again, because it's going further around the top, the velocity is higher, pressure's lower, and you get a lift. So there's two ways of doing that, getting lift on an airfoil. But it's all, relatively speaking, it's all related to Bernoulli's equation. The height's not different. But if you have an increase in velocity, then you have a decrease in pressure. And the more increase in velocity you have, the more decrease in pressure you have. And that pressure difference is enough to cause the lift on airplanes, on wings. So that's pretty interesting. Next time you fly in a plane, you can think about that. And if you've ever watched a plane, let me see if I can find a video here. Here we go. Oops. So, what you'll see is that they'll have these flaps on the end of the wing, and they also have ones in the front of the wing. And what they do is they extend these flaps to increase the curvature of the wing temporarily. Now you might say, well, why don't they do that during the entire flight? Well, because this causes a lot of drag, and you've got to run the engines, the efficiency of doing this is not very good. But for the process of slowing down your airplane and getting it to a low enough speed so when you hit the runway you don't crash. You extend these flaps. So I'm just kind of skipping through here. Let me see if I can, how many minutes have we got? We can just watch it here. I'll explain what's going on here. I'm going to mute it so I don't have to listen to it. Now, if you've ever watched an airplane taking off, they have flaps that they extend, but they extend them without the curvature. So all they're doing there is trying to increase the surface area of the wings. And you'll see how this gap gets bigger. There's actually air flowing between this gap and around the wings. So that's another way of increasing the lift. And it has to do with aerodynamics and keeping the flow attached to the wings. But as this plane is landing, the engines are running higher because the drag on the airplane is getting larger. But you can see how, again, they're extending these things. That little blip there was just to keep the airplane steady. But once they land, what will happen is you'll see that first let me stop there. What these are called spoilers. And basically that disrupts the flow over the wing and stops the lift from occurring. So once you land, you don't want lift anymore. You want it to stay down. So these spoilers basically ruin the aerodynamics of the wing. Okay. So once they've gotten on the ground, then let's see what happens next. They used to have thrust reversers on the engines. They don't use those as much as they used to. So thrust reversers were like pushing in the opposite direction. But you can see they're slowing down, they're putting the brakes on. And then once they get slow enough and they're ready to taxi to the terminal, they'll drop these things down and they'll pull these back in. Because now they're running so slow, there's no lift on the airplane anyway. So I think they're going to do this shortly before the end of the video. See, now they're on the taxiway. So the co-pilot's probably going to be, I don't know who steers this thing. Just make me a liar. Come on, come on. There we go. Now you can see how the wings are retracting back to their normal position. Okay, so there you go. Learned something new today. Let me close this thing. Oops. What was I doing here? So the my train of thought here. Conversion of pascals and atmospheric pressure. Well, atmospheric pressure is a certain number of pascals, and there's 100, 300, I think 1,325 pascals per 1 atmosphere. I think that was the number. There's also 14.7 pounds per square inch per atmosphere for 1 atmosphere. Okay. Yeah, you won't need to know the conversions. I'll be giving you everything. Okay, so let's, what I wanted to do in the last 20 minutes here was just to do a balloon problem. So let me download that particular module here. I just find this is an interesting problem. So you got a couple of balloon problems on your homework, so I'm going to do one balloon problem. Well, maybe it's not in one of these, but I'll still do it anyway. Well, yeah, I thought I had one. Maybe that's a homework problem that I'm thinking about. Okay, let's just look at this first problem. Okay, so we have a large balloon of mass, 226 kilograms, filled with helium gas until its volume is 325 meters cubed. Assume the density of air is 1.29 kilograms per meter cubed and density of helium is 1.179 kilograms per meter cubed. Draw a free body diagram of the balloon. Calculate the buoyancy force acting on the balloon. Find the net force on the balloon and determine whether the balloon will rise or fall after it is released. So this is just talking about how balloons work. So it's a buoyancy problem. So you've got your balloon here. And so acting upward, you've got your buoyancy force. Acting downward, you've got the weight of the helium and you've got the weight of the balloon. So if we did a free body diagram, we'd basically have buoyancy force going up, the weight of the helium going down, and the weight of the balloon going down. And if the buoyant force is greater than the weight of the helium and the balloon, then it's going to go up. And if it's the other way, then it's going to go down. So the first thing, that's my free body diagram. Calculate the buoyant force acting on the balloon. So the buoyant force is equal to the density of air, because that's what we're displacing with the balloon, times the acceleration due to gravity, times the volume displaced. So the density of air is 1.29 kilograms per meter cubed. The acceleration due to gravity is 9.8 meters per second squared, and the volume is 325 meters cubed. So we come up with the buoyant force. Oh, that reminds me. So as far as posting the test grades and uploading the solutions, I'm going to do that sometime today. I'm also going to do a video going through the solution to the test. I'll post that as well, so you can use that to study. And I'll do the same thing for the physics test. I'll upload you've got the grades for that, but I'll upload the solution. Okay, so let's see what this is. So the buoyant force is 4,110 newtons. So again, it's what we're displacing, which is air, acceleration due to gravity, the volume displaced. So now what we need to do is figure out, we know what the weight of the balloon is. That's given in the problem. Large balloon of 226 kilograms. So that's the mass, and you multiply by 9.8 meters per second. I guess you could multiply by 9.81 and we get 2,210 newtons. Okay, so that's at least the weight of the balloon can be supported by the buoyant force. Now you have to find the weight of the helium. So the density of the helium is equal to the mass of the helium divided by the volume of the helium. Well, the volume of the helium is the volume of the balloon. So we can figure out the mass of the helium is the density of helium times the volume of the helium, which is the balloon. And we go up and look for the density of helium, which is 0.179 kilograms per meter cubed times the volume, which is 325 meters cubed. So 325 times 0.179 is 58. Mass of the helium, 58. I'll give one more significant figure here, kilograms. So the weight of the helium is going to be equal to the mass of the helium times the acceleration due to gravity times 9.8. So that's 570 newtons. So the weight of the helium. So what we could do, if you applied Newton's second law, you'd have in the sum of the forces in the y direction, they're not necessarily equal to zero, because if the net force is going up, it's going to accelerate upwards. So we'd have that, and the forces, you'd have the buoyant force acting up, you'd have the weight of the balloon acting down, and you have the weight of the helium acting down. So if we do this net force here, we're going to have 4,110 newtons. This is the balloon handout. We're only going to have time to do one, so don't worry about turning it in. I just use the handout so I can have something to give me an example. Better watch out here with my fat fingers. You see I've been working on my grading. Okay, make sure I'm not pushing the wrong button here. Okay, so you got the buoyancy force going up. You've got the weight of the balloon going down, which is 2,210. You got the weight of the helium, which is 570. So if we take that, we get 570. So you get 1,330 newtons. It's positive, so that means it's going up. Now, I don't know if they asked us about acceleration or anything like that. What is the maximum additional mass the balloon can support in equilibrium? So what it's saying is because this number is positive, it's going to go up. Now, so that's saying that you could put some additional mass on there. So if we wanted to increase the, have a fourth term here, which would be the mass of the load. You could also have the weight of the load here. In our first case, there was no load. It was just the balloon and the helium. But a lot of times you have something hanging from the balloon. So we could call this the net force, 1,320 newtons up. So if you wanted to put a load on there to make the net force, what would be the load to make the net force equal to zero? Well, the answer would be that the load would be would be 1,320 newtons. So the corresponding mass would be the weight divided by the acceleration due to gravity. So you divide that by 9.8. and you get 135 kilograms. So that's how much additional mass you could have in addition to the balloon and the helium. So that's not a whole lot of mass. It could be a weather balloon where you couldn't have too many people under those circumstances. So that's how it works. It's a little bit different because Yeah, which ones do I want you to turn in? Because I don't think I'd worked all the problems in any of them. I'll tell you what, if you, let's go to here and look at this. I might give you some extra credit or something if you've actually done these. But so we did the buoyancy handout. So yeah, you can hand that one in. That one actually is, since we did all the problems on that one. The stress strain, I don't think we did any problems on that one. Out of that one, I did some examples in class. So just the buoyancy handout is the only one you really have to turn in. Just don't have enough time to get all of these things done. But you do have your homework. Okay, let's go back. If the balloon, if the mass of the load is less than the value, well, then it goes up. It says, what limits the height to which the balloon can rise? Well, what happens there is you can see that the buoyant force is dependent upon the density of the air. So as you go higher, the density of the air becomes less, and therefore the density of the air becomes less, so the buoyancy force becomes less. So there'll be some point where the balloon gets to a height and it will, the buoyancy force will just get lower and lower. And at that point, the buoyancy force equals the load, the weight of the balloon, the weight of what's in the balloon. So you think about helium balloons that you let go, which you shouldn't do, but people do. You know, they have this balloon, let go of the balloon. The balloon's going to go up, and it's going to, for one thing, another thing going to happen is because the pressure inside stays the same and the pressure outside gets less, that pressure difference between the in and the outside causes the balloon to expand. And so at some point, the balloon probably bursts at a certain altitude, and then it falls and kills fish and sea turtles. So if you ever looked at weather balloons, let's just find a picture of a weather balloon.